September 13, 1985. 38,000 feet above the Pacific Ocean, Major Doug Pearson sat in the cockpit of an F-15A Eagle climbing through thin atmosphere at an angle no fighter was designed to sustain. The aircraft shuddered as engines screamed against physics itself, pushing toward a release point that existed at the edge of what aerodynamics could tolerate. Beneath the centerline pylon hung a missile unlike any other in the American arsenal, a weapon designed not for enemy jets or ground targets but for something flying 200 miles straight up. At precisely the calculated moment, Pearson triggered the release. The ASM-135 anti-satellite missile ignited, accelerating vertically on a column of fire that punched through the stratosphere and into the vacuum beyond. 345 miles above Earth, the Salween P-78-1 satellite orbited in complete ignorance, a one-ton scientific spacecraft collecting solar data in what had always been considered an untouchable sanctuary. The missile's miniature homing vehicle separated from its booster stages, locked onto the satellite's infrared signature through a telescopic seeker, and began final approach corrections using 63 tiny rocket motors. At a combined closing velocity exceeding 32,000 miles per hour, the interceptor and satellite collided. There was no explosion in the Hollywood sense, only instantaneous disintegration as kinetic energy converted both objects into 285 pieces of glowing debris. For the first time in history, an air-launched weapon had destroyed an object in orbit. The age of sanctuary in space had ended, and adversaries who had built their entire military infrastructure on the assumption of orbital immunity suddenly faced a terrifying new reality. For 2 decades, Soviet military planners had operated under a comfortable certainty. Space was neutral territory, a domain where reconnaissance satellites, communications relays, and targeting systems could function without threat of direct attack. This assumption was not mere wishful thinking, but reasoned strategic assessment based on the technical barriers that seemed insurmountable. Destroying a satellite required hitting a target traveling at 17,000 miles per hour, hundreds of miles above the atmosphere, with trajectories calculated to within seconds and fractions of degrees. Soviet Marshal Nikolai Agarkov, chief of the General Staff throughout the early 1980s, had stated in classified briefings that American ASAT capabilities were at least a decade away from operational viability, giving the USSR ample time to develop countermeasures or matching systems. Intelligence assessments from the GRU consistently reported that while the United States possessed theoretical concepts for anti-satellite weapons, the integration challenges, tracking requirements, and interception velocities involved made near-term deployment unlikely. The confidence extended beyond theoretical analysis into operational doctrine. Soviet Cosmos reconnaissance satellites flew predictable orbits over American military installations, naval formations, and missile fields, transmitting targeting data back to command centers without meaningful defensive protocols. GLONASS navigation satellites, still in early deployment phases, operated on the premise that orbital infrastructure was beyond the reach of terrestrial weapons. This strategic blindness was compounded by what Western intelligence later termed sanctuary bias, a psychological condition where military planners become so invested in a domain's invulnerability that contradictory evidence gets systematically dismissed. When American officials began making public statements about ASAT development in the early 1980s, Soviet military journals published dismissive analyses suggesting the claims were propaganda designed to justify space militarization treaties that would lock in American disadvantage. Yet the arrogance was not entirely unjustified by contemporary standards. No nation had ever successfully engaged a satellite with a conventional weapon from an aircraft platform. The technical leap seemed genuinely impossible. The transformation of space from sanctuary to battlefield did not begin with the F-15 ASAT system, but with a far more primitive and terrifying predecessor that Soviet intelligence had catastrophically underestimated. In the early 1960s, as the first reconnaissance satellites began providing unprecedented intelligence on Soviet missile deployments and nuclear facilities, the Pentagon faced an urgent question. How could America defend against enemy satellites that would guide strikes against continental targets during nuclear war? The answer emerged as Program 437, a weapons system so radical that its very existence challenged fundamental assumptions about where warfare could occur. Beginning in 1963, the United States deployed nuclear-tipped Thor missiles on Johnston Atoll and Kwajalein Atoll in the Pacific, modified for vertical launch toward orbital targets. These were not precision interceptors but instruments of overwhelming force, mounting W-49 thermonuclear warheads with yields up to 1.45 megatons. The operational concept was simple in theory and apocalyptic in execution. When a Soviet satellite passed overhead within engagement geometry, a Thor would launch vertically, climb beyond the atmosphere, and detonate its warhead in proximity to the target. The blast effects in vacuum were different from atmospheric explosions, but no less destructive, generating intense X-ray and gamma radiation that would fry electronics, ablate solar panels, and induce structural failure through thermal shock. Between 1964 and 1970, Program 437 conducted multiple combat training launches that demonstrated feasibility, including several tests that brought warheads within lethal proximity of actual rocket bodies and satellites in low and medium Earth orbit. On May 29, 1964, the system was declared at initial operating capability, meaning nuclear-armed Thor missiles sat on 24-hour alert, ready to prosecute orbital targets on command authority from the National Command Authority. Soviet strategists knew Program 437 existed after President Lyndon Johnson publicly revealed it during a campaign speech in September 1964, yet they fundamentally miscalculated its implications. Internal Soviet assessments suggested the nuclear ASAT was too crude to be strategically relevant, requiring launch preparation times that would allow satellite operators to execute evasive maneuvers and generating electromagnetic pulse effects that would damage American satellites as well. What these assessments missed was the psychological dimension. The United States had demonstrated willingness to nuclearize space warfare, establishing a precedent that orbital infrastructure was not merely vulnerable but actively targeted in contingency planning. The nuclear approach had severe limitations that became increasingly apparent as satellite constellations grew in number and value. Detonating megatons in orbit risked cascading damage to friendly spacecraft, violated emerging international norms, and generated political fallout that constrained operational flexibility. What the American defense establishment needed was a precision system capable of selectively destroying individual satellites without collateral effects, a weapon that could be used in limited conflicts below the nuclear threshold. This requirement drove development of the ASM-135 ASAT, a program that married existing F-15 performance with cutting-edge guidance technology to create the world's first conventional direct-descent anti-satellite weapon. The system's architecture reflected lessons learned from ballistic missile defense programs and aerospace intercept studies conducted throughout the 1970s. The missile itself was a two-stage solid fuel design measuring 18 feet in length and weighing 2,600 pounds at launch. The first stage, a modified AGM-69 SRAM motor, provided initial boost out of the dense lower atmosphere. The second stage accelerated the weapon into exoatmospheric trajectory, achieving velocities exceeding 11,000 miles per hour. But the revolutionary component was the miniature homing vehicle, a 50-pound autonomous interceptor that separated from the booster stages and prosecuted the final engagement phase independently. The MHV carried no explosive warhead because at orbital closing velocities, kinetic energy alone was sufficient to vaporize any satellite. Its guidance system used a long-wave infrared telescope cooled to cryogenic temperatures, allowing it to detect and track the faint heat signature of satellites against the absolute cold of space. 63 small hydrazine thrusters arranged around the vehicle's body provided omnidirectional maneuvering authority, enabling course corrections during the terminal approach phase that lasted mere seconds. The entire engagement sequence, from F-15 launch at supersonic speed and high altitude to satellite impact 200 miles higher, required coordination between ground-based tracking radars, onboard inertial navigation systems, and autonomous terminal guidance algorithms that represented the cutting edge of 1980s aerospace technology. The F-15 platform itself was critical to the system's effectiveness in ways that Soviet analysts initially failed to appreciate. The Eagle's sustained climb capability allowed it to reach launch altitudes above 38,000 feet, while maintaining sufficient energy for the dramatic zoom climb maneuver required to optimize missile trajectory. Unlike ground-based launchers that telegraphed intentions through hours of visible preparation, the F-15 ASAT could be launched from any suitable airfield with minimal notice, providing strategic ambiguity about American intentions and complicating Soviet satellite protection planning. The aircraft's advanced avionics, including the APG-63 radar and central computer, handled pre-launch calculations for intercept geometry based on real-time satellite tracking data fed from ground stations and early warning networks. Operational procedures called for the F-15 to accelerate to Mach 1.5 and execute a 3.5G pull-up into a steep climb angle exceeding 65 degrees, releasing the missile at the apex of this ballistic arc to maximize the weapon's kinetic energy and altitude potential. The physical stress on both aircraft and pilot was extreme, pushing the F-15's structural limits and requiring pilot proficiency in flight regimes never contemplated during the aircraft's original design. Test programs conducted between 1982 and 1985 involved 17 captive carry missions, where inert ASM-135 missiles were flown through realistic engagement profiles without actual launch, validating aerodynamic models and proving the aircraft could survive the asymmetric loading of the massive pylon-mounted weapon. These tests took place at the Western Test Range, operating from Vandenberg Air Force Base in California, where radar tracking stations and telemetry networks could monitor every phase of the intercept sequence. By mid-1985, the program had accumulated sufficient data to attempt a live engagement against a real orbital target, leading to the selection of Solwind P-78-1 as the designated sacrifice. If you appreciate discovering Cold War secrets hidden for decades, consider subscribing for future declassified revelations. The choice of Solwind as target was itself revealing of the strategic calculations driving American ASAT development. Launched in February 1979, Solwind was a scientific satellite designed to study solar activity and X-ray emissions from the Sun's corona, operating in a polar orbit at an altitude of 345 miles. By 1985, several of its instruments had failed, making it scientifically marginal but still functional enough to provide realistic tracking and engagement characteristics. More importantly, from a targeting perspective, its orbital parameters closely matched those of Soviet reconnaissance and electronic intelligence satellites, particularly the Cosmos series that conducted photographic surveillance and signals intelligence collection over American territory. The polar orbit, with inclination near 90 degrees, meant Solwind passed over both poles during each revolution, providing coverage of high-latitude regions where Soviet early warning radars and strategic forces were concentrated. This orbit type was favored for reconnaissance because it allowed systematic coverage of the entire planet as Earth rotated beneath the satellite's fixed orbital plane. By demonstrating the capability to destroy a satellite in polar orbit at medium altitude, the United States sent an unmistakable message about which Soviet spacecraft were now at risk. The engagement itself was a masterpiece of aerospace coordination. Major Pearson's F-15A, tail number 7784, launched from Vandenberg with the ASM-135, mounted on a reinforced centerline pylon that had been stress-tested to handle the weapon's unique loading characteristics. Ground controllers fed real-time tracking data to the aircraft's mission computer, calculating the precise launch window that would align the missile's trajectory with Solwind's orbital path. The interception required predicting not just where the satellite would be several minutes in the future, but accounting for Earth's rotation, atmospheric drag effects on the missile's trajectory, and the slight but measurable gravitational perturbations that affected both target and interceptor. At the computed release point, Pearson triggered the launch, and the ASM-135's first stage ignited with 22,000 pounds of thrust, separating from the aircraft and pulling away in a vertical climb that left a contrail visible for hundreds of miles. The second stage ignited at programmed altitude, accelerating the miniature homing vehicle to its terminal velocity. Onboard sensors acquired Solwind's infrared signature at a range of several miles, confirming target lock. The terminal engagement phase lasted approximately 8 seconds from acquisition to impact. The MHV's guidance computer processed target angle data at 20 times per second, commanding thruster firings to null out lateral velocity components and achieve a collision course. At 21:42 GMT, the inevitable mathematics of orbital mechanics reached their conclusion. The homing vehicle struck Solwind at a combined velocity exceeding 9 miles per second, converting both objects into an expanding debris cloud that would remain in orbit for years, a permanent reminder that space was now contested territory. Soviet reaction to the successful ASAT test was carefully controlled in public statements but bordered on panic in classified military channels. Within 48 hours of the interception, the USSR lodged formal diplomatic protests claiming the test violated the spirit of the Outer Space Treaty and represented dangerous militarization of the cosmos. But the private assessments told a different story. Declassified intelligence reports from the period, released through Freedom of Information Act requests in the late 1990s, reveal that Soviet space forces conducted emergency reviews of every military satellite's vulnerability to similar attacks. The analysis was damning. Nearly 70% of operational Soviet military satellites orbited at altitudes within the demonstrated reach of the ASM-135 system, including critical cosmos reconnaissance platforms, Molniya communications satellites in highly elliptical orbits that dipped into the engagement zone at perigee, and early-generation GLONASS navigation satellites. Perhaps most troubling from the Soviet perspective was the realization that the F-15 ASAT represented asymmetric capability America could deploy in numbers. The United States Air Force operated hundreds of F-15s across multiple air wings, and while not all could be configured for the ASAT mission, the potential to generate dozens of simultaneous engagement platforms created a targeting calculus nightmare for satellite protection planners. A Soviet military space officer, later identified through defector testimony as Colonel Viktor Yesenov of the Strategic Rocket Forces Space Directorate, wrote in a classified 1986 assessment that the Americans have demonstrated the capability to blind us at will, removing decades of investment in orbital reconnaissance at the cost of aircraft sorties we cannot prevent. The psychological impact extended beyond immediate military concerns. Soviet doctrine had invested heavily in the concept of space-based reconnaissance as the foundation for deep strike operations against NATO forces during the opening phases of any European conflict. The ability to locate American carrier battle groups, track armor concentrations, and identify logistics nodes depended entirely on satellites that were now revealed as fragile and exposed. The loss of assured space superiority fundamentally undermined confidence in operational plans that had been developed over 20 years. The technical specifications of the ASM-135 system represented a convergence of technologies that Soviet engineers had believed were still years from operational maturity. The miniature homing vehicle's infrared seeker operated in the 8 to 12 micron wavelength band, optimized to detect the subtle thermal emissions from satellite sun-facing surfaces and electronic components. The seeker's sensitivity was extraordinary, capable of acquiring targets with temperature differentials as low as 50 degrees Kelvin against the background of deep space. The guidance processor, built using radiation-hardened electronics developed for strategic missile systems, executed proportional navigation algorithms that calculated optimal intercept trajectories in real time, adjusting for target maneuvering and trajectory perturbations. The 63 hydrazine thrusters were arranged in clusters that provided thrust vectoring in all three axes, with individual nozzles producing between 0.5 and 2 pounds of thrust on command cycles measured in milliseconds. This level of precision maneuvering in vacuum, where aerodynamic control surfaces were useless, and every action produced an equal and opposite reaction that had to be compensated, represented aerospace control theory implemented at the highest level. Soviet attempts to reverse engineer the capability based on telemetry intercepts and analysis of debris patterns revealed just how sophisticated the American approach had been. The homing vehicle's spin stabilization technique, maintaining rotational velocity to preserve gyroscopic stability while simultaneously executing translational maneuvers, required control algorithms that were beyond contemporary Soviet spacecraft technology. The entire engagement sequence from F-15 launch to satellite impact consumed less than 5 minutes, providing minimal warning time and essentially no opportunity for defensive maneuvering by the target satellite. This compression of the decision-action cycle was strategically critical. In conflict scenarios, American commanders could theoretically order multiple simultaneous ASAT strikes against a prioritized target list, destroying an adversary's space-based intelligence and communications infrastructure before meaningful countermeasures could be implemented. The operational implications were staggering. Control of space directly translated to control of information, and control of information determined the outcome of every other military operation across every other domain. The ASM-135 program was not merely a weapon system, but a statement about American technological confidence and strategic intent. The public demonstration sent a clear message to potential adversaries. The United States possessed both the capability and willingness to deny space assets to any nation that threatened American interests. This extended beyond the Soviet Union to include any future adversary that might emerge in the decades ahead. The system's development path revealed the depth of American investment in maintaining space superiority. Project funding between 1977 and 1988 totaled approximately $5 billion in period currency, covering research, development, testing, and evaluation of not just the missile system but the entire engagement architecture. This included upgrades to ground-based tracking radars at multiple sites across the Pacific and continental United States, development of dedicated mission planning software that could calculate intercept geometries for arbitrary target orbits, and training programs that qualified dozens of Air Force pilots in the extreme flight regimes required for ASAT launch profiles. The program established a space surveillance network of ground-based radars and optical telescopes that tracked every object larger than 10 centimeters in low Earth orbit, maintaining a constantly updated catalog of orbital elements for potential targets. This surveillance infrastructure provided the foundational data necessary for engagement planning, allowing military commanders to know at any given moment which satellites were passing over sensitive areas and which could be prosecuted if conflict escalated. The existence of this targeting infrastructure was itself a form of strategic messaging. America was watching, cataloging, and maintaining the ability to act decisively against orbital threats. Yet the ASM-135 represented only one approach to space warfare, and perhaps not the most strategically significant in the long term. Concurrent with the development of kinetic kill vehicles, the Pentagon invested heavily in directed energy weapons and electronic warfare systems designed to degrade or destroy satellites without generating the problematic orbital debris that kinetic impacts created. The Miniature Vehicle Technology Program, separate from but related to ASM-135 development, explored laser tracking and targeting systems that could precisely illuminate satellites for ranging and designation. Ground-based lasers at facilities like the Mid-Infrared Advanced Chemical Laser at White Sands Missile Range in New Mexico achieved sufficient power levels to dazzle or permanently blind optical sensors on low-orbit reconnaissance satellites, providing a reversible ASAT capability that could be employed below the threshold of overt warfare. Classified programs with code names like MIRACL, Zenith Star, and Talon Gold explored space-based laser platforms that could engage targets without the trajectory limitations imposed on ground-based systems. While technical challenges prevented deployment of orbital laser weapons during the Cold War era, the research established technological foundations that would mature in subsequent decades. Electronic warfare approaches offered even more subtle and strategically flexible options. Radio frequency jammers could disrupt satellite communications and command links, effectively rendering spacecraft inoperable without physically destroying them. GPS jamming and spoofing technologies allowed adversary navigation signals to be degraded or corrupted, undermining the precision guidance systems that modern military operations increasingly depended upon. These non-kinetic approaches had the advantage of deniability and reversibility, allowing space warfare operations to be conducted without the escalatory risks of permanent satellite destruction. The combination of kinetic, directed energy, and electronic warfare capabilities created a comprehensive anti-satellite arsenal that addressed different threat scenarios and operational requirements across the spectrum of conflict intensity. The Soviet response to demonstrated American ASAT capability took multiple forms, ranging from diplomatic initiatives to accelerated development of indigenous space weapons. At the diplomatic level, the USSR proposed a series of treaties and confidence-building measures designed to ban anti-satellite weapons and prevent the weaponization of space. These initiatives, presented at United Nations forums and bilateral arms control negotiations, argued that space militarization threatened strategic stability and increased the risk of accidental conflict escalation. The American position was more nuanced, acknowledging concerns about debris generation and crisis instability, while maintaining that space weapons were legitimate defensive capabilities necessary to protect vital national security satellites from attack. The real concern driving Soviet diplomacy was not abstract principle but concrete military vulnerability. By the mid-1980s, the USSR had deployed approximately 150 military satellites supporting reconnaissance, communications, navigation, early warning, and electronic intelligence missions. These spacecraft represented decades of investment and constituted the central nervous system of Soviet military power projection. The loss of space-based reconnaissance capability would leave Soviet forces effectively blind to American carrier movements, bomber dispersal patterns, and missile deployment changes, removing the targeting data necessary for preemptive strike options that formed the core of Soviet nuclear war planning. Similarly, loss of Malnya communications satellites would sever command and control links to submarine forces, strategic bomber bases, and mobile missile units, potentially paralyzing the ability to execute coordinated military operations across the USSR's vast territory. The vulnerability was asymmetric because Soviet satellites, built with shorter design lives and greater mass margins due to less advanced electronics and materials technology, were easier targets than their American counterparts. American reconnaissance satellites like the KH-11 digital imaging system operated at higher altitudes and employed more sophisticated maneuvering capabilities, making them harder to track and engage. This asymmetry meant that in any space warfare exchange, the Soviet Union stood to lose more faster and with less ability to reconstitute lost capabilities through rapid launch of replacement satellites. Soviet countermeasures took several directions, each revealing different assumptions about future space conflict. The first response was to accelerate development of the co-orbital ASAT system that had been in testing since the late 1960s. This system, designated IS or Istrabital Sputnikov in Russian, used a hunter-killer satellite launched on a Cyclone 2 rocket that would maneuver into close proximity with target satellites before detonating a fragmentation warhead. Between 1968 and 1982, the Soviet Union conducted 20 co-orbital intercept tests with mixed results, achieving successful target destruction in approximately two-thirds of attempts. The system had severe limitations compared to the American direct ascent approach. Launch preparation required hours of visible activity at Baikonur or Plesetsk cosmodromes, telegraphing intentions and allowing potential targets to execute evasive maneuvers. The Interceptor satellite required multiple orbits to achieve rendezvous geometry with most targets, providing ample warning time measured in hours rather than the minutes available against an F-15 ASAT launch. Most critically, the co-orbital approach was ill-suited for rapid engagement of multiple targets or crisis scenarios where immediate response was necessary. Despite these limitations, the USSR continued development and declared the IS system operational in 1973, maintaining a cadre of trained launch crews and pre-positioned interceptor satellites that could be activated on short notice. The second Soviet response focused on satellite hardening and defensive maneuvers. Engineers redesigned reconnaissance and communications satellites with more robust structures, redundant systems, and radiation shielding designed to improve survivability against both kinetic impacts and directed energy weapons. Operational procedures were revised to incorporate random orbital maneuvering using onboard propulsion, making trajectory prediction more difficult for potential attackers. Some high-value satellites were equipped with decoys and radar reflectors designed to complicate target identification and tracking. These measures increased satellite mass and cost while reducing operational lifetimes due to fuel expenditure on defensive maneuvers, but Soviet planners deemed the trade-offs acceptable given the existential threat that American ASAT capabilities represented. The third and most ambitious Soviet response involved development of directed energy weapons specifically optimized for anti-satellite missions. The Terra-3 laser complex at Sary-Shagin in Kazakhstan, originally developed for ballistic missile defense research, was adapted to track and illuminate low-orbit satellites with focused carbon dioxide laser energy. While insufficient to destroy satellites outright, the system could damage sensitive optical sensors and solar panels, degrading spacecraft functionality. More ambitious was the Polyus Orbital Weapons Platform, a massive spacecraft designed to carry megawatt-class lasers or particle beam weapons capable of destroying satellites and possibly intercepting ballistic missiles. The Polyus program represented the pinnacle of Soviet space weapons ambition, a 30-ton combat platform that would operate in low orbit with sufficient power generation and thermal management to sustain repeated engagements. The spacecraft was launched on the maiden flight of the Energia heavylift rocket in May 1987, but a malfunction during orbit insertion caused Polyus to tumble and execute its retrograde burn prematurely, sending it into the Pacific Ocean rather than orbit. The failure effectively ended Soviet dreams of deployed orbital battle stations, a victim of the technical complexity and enormous resource demands that space weapons systems imposed. These programs collectively demonstrated that while the Soviet Union possessed sophisticated aerospace engineering capabilities, the American lead in guidance systems, miniaturization, and integration of space and air power platforms provided decisive advantages in ASAT warfare. The F-15 ASAT could be launched on short notice from dispersed bases, prosecute targets within minutes, and be recovered for reuse, while Soviet systems required conspicuous launch preparations, longer engagement timelines, and single-use interceptors that consumed entire rockets for each mission. The asymmetry was strategic as well as technical, reflecting deeper differences in how the superpowers approached military space operations. The broader implications of demonstrated anti-satellite capability extended far beyond the bilateral competition between the United States and Soviet Union. The 1985 Solwind intercept fundamentally changed international perceptions about space as a domain of warfare. Prior to that demonstration, space had been treated in practical terms as an arena of competition but not direct combat, where satellites maneuvered and jockeyed for orbital positions but did not actively engage each other. The successful kinetic kill removed any remaining illusions about sanctuary in orbit. Military planners worldwide recognized that future conflicts between advanced nations would almost certainly include space warfare as a critical dimension, potentially preceding and enabling operations in terrestrial domains. This recognition drove proliferation of space surveillance capabilities and counterspace technologies far beyond the superpowers. China initiated serious work on anti-satellite systems in the late 1980s, leading to the controversial 2007 test destruction of the Fengyun 1C weather satellite that generated more than 3,000 pieces of trackable debris, and effectively demonstrated Chinese ASAT capability at ranges extending to medium Earth orbit. India conducted its own ASAT test in 2019, destroying a low-orbit satellite with a direct descent missile launched from Kalam Island, joining the exclusive club of nations with proven kinetic intercept capabilities. Even smaller nations and non-state actors recognized that space operations represented both opportunity and vulnerability, leading to investments in capabilities ranging from ground-based laser dazzlers to cyber attacks against satellite ground stations. The diffusion of ASAT technology created new strategic instabilities and arms race dynamics that persisted long after the Cold War ended. The economic dimensions of space warfare capability were equally significant. Satellites represented enormous capital investments, with modern reconnaissance, communications, and navigation spacecraft costing hundreds of millions to billions of dollars each when accounting for development, launch, and operational expenses. The prospect of these assets being destroyed in conflict created powerful incentives for both defensive measures and deterrent postures. Insurance markets for commercial satellites developed risk models incorporating probability of attack during regional conflicts, driving up costs and potentially limiting civilian space commerce during periods of tension. Military space budgets expanded dramatically to fund redundant constellations, hardening measures, and rapid reconstitution capabilities designed to ensure mission continuity even after initial losses. The United States Space Command, established in 1985 coincident with the successful ASAT test, received expanding authorities and resources to coordinate space defense and offensive operations across service branches. By 2019, space warfare had become sufficiently important that the United States established a separate space force as an independent military service, reflecting recognition that orbital operations required dedicated organizational focus and specialized expertise. The elevation of space to domain equivalency with air, land, sea, and cyber operations marked the culmination of strategic thinking that began with those early ASAT programs of the 1960s and achieved operational validation with the ASM-135 intercept of Solwind. The intellectual journey from viewing space as benign observation platform to treating it as contested warfighting domain represented one of the most significant strategic transitions of the late 20th century. The technical lessons learned from ASM-135 development informed subsequent American space weapons programs, even after the direct descent ASAT was terminated in 1988 due to congressional budget restrictions and arms control concerns. The miniature homing vehicle technology migrated into ballistic missile defense programs, particularly the brilliant Pebbles concept of the Strategic Defense Initiative that envisioned constellations of small space-based interceptors. The precision guidance algorithms developed for satellite intercept found application in hypersonic weapon programs, where engaging maneuvering targets at extreme velocities required similar computational approaches. The integration of ground-based tracking networks with airborne launch platforms established architectural patterns that influenced development of Aegis ballistic missile defense and THAAD systems, which employed similar kill chain concepts adapted for different threat sets. Perhaps most importantly, the ASM-135 program validated the feasibility of hit-to-kill interception using kinetic energy alone, without need for explosive warheads or nuclear effects. This kinetic kill approach became the dominant paradigm for missile defense and continues to inform contemporary space weapons concepts. The engineering confidence gained from successfully destroying Solwind at 345 miles altitude, with a 50-pound vehicle traveling 11,000 miles per hour, provided proof that precision guidance technology had matured to the point where seemingly impossible intercepts were not only feasible but reproducible and operationally relevant. Modern space warfare capabilities have evolved considerably beyond the technologies demonstrated in 1985, but the fundamental strategic principles remain unchanged. Control of space translates directly into military advantage in every other domain because contemporary warfare depends absolutely on satellite-enabled capabilities. Precision strike weapons require GPS navigation signals to achieve their advertised accuracy. Intelligence, surveillance, and reconnaissance operations depend on satellite imagery and signals intelligence collection from orbital platforms. Communication systems that coordinate joint operations across continents and oceans rely on satellite relay links. Early warning of ballistic missile launches comes primarily from infrared sensors aboard satellites in geosynchronous orbit. Remove these capabilities, and modern military forces revert to operating methods not substantially different from World War II-era blind navigation, area bombardment, and communications by radio with all its limitations and vulnerabilities. This dependence creates enormous incentive to protect space assets while simultaneously targeting adversary spacecraft, driving a competitive dynamic that persists despite arms control efforts. The 2019 establishment of the United States Space Command as a combatant command with geographic responsibility for orbital operations above 100 kilometers altitude formalized what the ASM-135 program had demonstrated 3 decades earlier. Space is not a sanctuary but a warfighting domain where conflict will occur and where American forces must be prepared to fight and win. Current doctrine emphasizes space superiority as a prerequisite for joint operations, explicitly acknowledging that space control is as critical as air superiority in enabling surface forces to operate effectively. The transition from viewing ASAT weapons as exotic capabilities at the edge of technical feasibility to treating space warfare as routine military planning reflects the maturation of strategic thinking about orbital operations. The proliferation of counterspace capabilities beyond the United States and Russia has created a multipolar space warfare environment qualitatively different from Cold War bipolar competition. China's 2007 ASAT test not only demonstrated technical capability, but signaled strategic intent to challenge American space dominance. Subsequent Chinese developments include directed energy weapons capable of dazzling or blinding satellite sensors, cyber capabilities targeting satellite ground stations and control networks, and a growing constellation of satellites with potential proximity operations capability that could be used for inspection, servicing, or attack missions. Russia has continued developing co-orbital interceptors and deployed ground-based electronic warfare systems like Tirada-2 and Pol-21, specifically designed to jam military satellite communications in various frequency bands. The Noodle Direct Descent ASAT system, successfully tested multiple times since 2014, provides Russia with capabilities similar to the retired American ASM-135, demonstrating that kinetic intercept technology has matured and proliferated across potential adversaries. India's 2019 mission Shakti ASAT test established a fourth nation with proven kinetic anti-satellite capability, and public statements from Indian defense officials suggest development of more advanced systems targeting higher orbital regimes. Even nations without dedicated ASAT programs possess latent capabilities through dual-use technologies. Any country with intermediate-range ballistic missiles could potentially adapt those systems for satellite intercept missions, particularly against low-orbit targets. Advanced cyber capabilities provide another path to space warfare effects without requiring expensive kinetic systems, as demonstrated by numerous incidents of satellite hijacking, signal interference, and ground station intrusions attributed to state and non-state actors. The debris problem created by kinetic anti-satellite weapons has emerged as a constraining factor on their operational employment, though perhaps not an absolute deterrent. The 1985 Solwind intercept generated 285 trackable debris pieces, most of which remained in orbit for years afterward, creating collision hazards for other spacecraft, including those belonging to the attacking nation. The 2007 Chinese ASAT test produced more than 3,000 debris fragments, some of which will remain in orbit for decades, significantly increasing collision risk in the affected orbital planes. This debris persists as a long-term hazard because there is no practical way to clean it up using current technology. Each fragment, traveling at orbital velocity, carries sufficient kinetic energy to catastrophically damage any spacecraft it strikes. The possibility of cascading collisions, where debris from one impact creates more debris that triggers additional collisions in a runaway process known as Kessler syndrome, threatens to render certain orbital regions effectively unusable. This has led to increased emphasis on non-kinetic ASAT approaches that achieve reversible or temporary effects without generating persistent debris. Electronic warfare systems that jam or spoof satellite signals, cyber attacks against ground control infrastructure, and directed energy weapons that degrade components without catastrophic breakup all offer space warfare capabilities with reduced debris generation. However, the strategic calculation during actual conflict may favor kinetic weapons despite debris concerns if the immediate military advantage of destroying critical enemy satellites outweighs long-term orbital sustainability considerations. A nation facing conventional military defeat might rationally decide that generating orbital debris is an acceptable cost for eliminating the space-based reconnaissance and communication systems enabling enemy operations. This possibility ensures that kinetic ASAT weapons remain relevant despite environmental concerns, particularly for nations that assess they have less to lose from orbital debris than from military defeat in terrestrial domains. The integration of space warfare into broader military planning continues to deepen as dependence on satellite-enabled capabilities increases rather than decreases. Modern precision strike weapons like the Joint Direct Attack Munition require continuous GPS signals throughout their flight to achieve published accuracy of less than 10 meters. Communication systems for beyond line-of-sight coordination between headquarters and forward units depend on satellite links that cannot be easily replaced by terrestrial alternatives given the ranges involved. Intelligence collection relies heavily on satellite imagery with resolution sufficient to identify individual vehicles and weapon systems, providing targeting data that cannot be obtained through other means. Early warning of ballistic missile launches comes primarily from the space-based infrared system constellation of satellites in geosynchronous orbit that detect missile plumes in boost phase. Naval operations over open ocean depend on satellite communications and navigation in the absence of terrestrial infrastructure. All of these dependencies create vulnerabilities that adversaries can exploit through counterspace operations. The strategic implication is clear. Future conflicts between advanced military powers will begin with efforts to degrade or destroy enemy space capabilities, potentially minutes or hours before overt hostilities commence in terrestrial domains. Space warfare will not be a sideshow to terrestrial conflict, but the opening phase that shapes everything that follows. Forces operating without space support will face opponents who can see continuously while remaining blind themselves, who can communicate freely while their own networks fail, and who can strike with precision while reduced to area weapons of doubtful effectiveness. These asymmetries are so decisive that maintaining space superiority has become the prerequisite for military operations rather than a supporting element, inverting the traditional relationship between space and terrestrial combat. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink. The transformation of space from sanctuary to battlefield represents one of the most consequential strategic shifts in military history, comparable to the advent of air power or nuclear weapons in its implications for how wars are fought and deterred. What began with crude nuclear-tipped missiles in the 1960s evolved through precision kinetic interceptors in the 1980s into today's sophisticated multi-domain approach combining kinetic, directed energy, electronic, and cyber capabilities. The successful destruction of Solwind on September 13, 1985, marked the moment when theoretical space warfare concepts became operational reality, forcing adversaries to confront the uncomfortable truth that their orbital infrastructure was vulnerable and that sanctuary in space had always been an illusion. The arrogance of assuming space would remain neutral territory collapsed when Major Doug Pearson released that ASM-135 missile and proved that American technology could reach into the void and destroy objects traveling at orbital velocity hundreds of miles above Earth. Soviet planners who had invested decades and vast resources building military satellite constellations suddenly faced the prospect of losing those capabilities in the opening minutes of any conflict, undermining the foundations of their operational doctrine and strategic planning. The lesson transcended the specific weapon system. American technological innovation and integration capabilities could solve problems that adversaries believed were impossible, could turn theoretical concepts into deployed systems faster than intelligence assessments predicted, and could fundamentally alter the strategic balance through capabilities that opponents could not match. The age of space sanctuary ended not with diplomatic treaty or gradual erosion, but with decisive demonstration that satellites were targets, that America possessed weapons to destroy them, and that no nation could assume its orbital infrastructure was beyond reach. Future adversaries watching debris from Solwind continue to orbit years after the intercept, understood that American dominance extended beyond terrestrial domains into the cosmos itself, and that any future conflict would be decided not just by forces on land, sea, and air, but by control of the ultimate high ground hundreds of miles overhead, where satellites provided the eyes, ears, and nervous system of modern warfare.